Hello, today we are continuing in our A-level physics revision series looking at the charge and mass of an electron. We must remember that at this stage scientists were not aware of electrons, and indeed they considered that atoms, whatever they were some kind of solid, indivisible thing that you couldn't divide. It was a basic element of matter. And it's on that basis that we have to consider what happened in 1876, where an experiment was being performed where you take a glass tube, you evacuate it, that is, you suck all the air out, and then you have an electric current. Well, it won't flow because, of course, there's a gap between here, but you put a very, very high voltage. A single battery won't usually do. You need a very high voltage, and I've connected them up the wrong way round. That's the negative end of the battery, that's the positive end. So this is negative and this is positive end. And what was seen, if you evacuate the glass tube, what was seen was rays seem to emanate from this terminal here, and the negative terminal is called the cathode, and the positive terminal is known as the anode. And those rays which seemed to come out of the cathode were called cathode rays. As we shall discover, cathode rays were in fact electrons, but nobody knew that at the time. Now, there was a very important experiment that was done by J Thomson in the very late 1800s. And it was basically a repeat of this experiment, but I'll just draw it again. Here's the glass tube again. Here is the cathode and the anode connected to a very high voltage supply. The tube is evacuated and a very small amount of hydrogen is inserted. Not very much, just a very small amount of hydrogen. But what J Thomson did was he put two more electric plates on either side of the tube, such that this plate was positively charged and this plate was negatively charged. Essentially, you just connect those two plates via a battery, and such that that's negatively charged and that's positively charged. Now, he was looking at the cathode rays, which were kind of going across like that, and what he noticed is when he switched on this field between these two plates, he noticed that the cathode rays seemed to divert upwards like that. And he concluded from that that whatever those rays were, they must be negatively charged. They must be negatively charged because they're being attracted to the positively charged plate. And we know that like charges repel, but unlike charges attract. So if these charges are attracting one another, then the negative charge is being attracted to the positively charged plate. Now, J Thomson knew that the only thing that was inside this glass tube was the hydrogen. And hydrogen, he knows, is neutral. There is no charge on hydrogen. Atoms are not charged, they are neutral. And molecules are not charged, they are neutral. So he concluded that whatever it was that was diverting must be a part of an atom. And that was where J Thomson was the first person really to get the idea that an atom actually isn't indivisible. It contains something within it which is negatively charged, and it's that negatively charged thing that is being diverted towards the positively charged particle. J Thomson said that if there was a neutral atom inside which there was a negative something, then there must also be a positive something. If that's negative, then there must be something positive such that when the two combine, they form a neutral atom. And if there was something positive, then surely there should be something diverting towards the negative plate. But at first sight, there didn't seem to be. It was only much later that he realised that there was something just beginning to divert in the downwards direction, but not by very much. And he concluded that the reason for this was that the particles that were moving downwards were very much heavier than the particles moving upwards. The heavier the particle, the more difficult it is to divert it in an electric field. But the lighter the particle, the easier it is to divert it. So he concluded that the negative particles must be very light and the positive particles must be very heavy. So the atom, which is neutral, must contain the bulk of the material is positively charged, but the small part of the material is negatively charged. And these negatively charged bits of an atom subsequently became known as electrons. And what we now know of the positive part of the atom is, of course, the protons which occupy the nucleus. We shall learn more about that in later videos. But now we're going to look at how electrons can be produced not by having necessarily a huge voltage, which is what you need here, but by what's called thermionic emission. And what you do is you take a heater in the form of a coil that's going to heat the cathode, and here is the cathode. This all has to be inside the glass jar, which has to be obviously evacuated. That is going to be the anode, and this, as I said, is the cathode. And we can now connect the cathode and the anode to a smaller power source now, because the real source of the electrons is going to be achieved by heating the cathode, so that the electrons are released by what's called thermionic emission. And what we can do is take this anode here, and if we make it an anode like this, where there's a small circular, there's a small circular hole in the anode here, then what will happen is that the electrons, the cathode rays, which we now know to be electrons, will speed across to the anode. And here on the bigger diagram, as they reach the anode, some of them of course will hit the anode, but some of them will go through the hole in the middle. And that is effectively an electron gun. It's the means by which you can create electrons by heating the cathode, so that you give electrons energy. They are then released, they cross the tube which has been evacuated, they hit the anode, but some of them at least will go past or through the hole in the anode, and that becomes a source of electrons. We're now going to look at the energy of an electron. We have already seen in previous videos that if you take a positive and negative plate and you take a positive charge, Q, and put it in that plate, the charge will accelerate, if it's positively charged, towards the negative plate. And what we can say is that if the potential difference across those plates is V, then the energy of that charge will equal Q times V. And that is expressed in joules. Q will be in coulombs, the charge on the particle. V will be in volts, the potential across the plates. Now there's a new unit of energy that's been created, and it's called an electron volt. It's written like that. And basically, 1 electron volt is what you get if you take 1 electron, which has the charge of 1 electron, and you put it in a field which has a potential difference of 1 volt. That is 1 electron volt. And an electron volt is a unit of energy. But how does it compare to joules? Well, let's see. Strictly what we ought to say is that energy equals the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs, times the voltage, which is 1. And so that is 1.6 times 10 to the minus 19 joules. So 1.6 times 10 to the minus 19 joules is the same as 1 electron volt. So an electron volt is a very small amount of energy, but when you're talking about the energies of electrons or protons, it's very often easier to talk in terms of electron volts, because then you don't have a term with 10 to the minus 19 on it, and the whole thing becomes much more manageable. So if you want to convert electron volts to joules, you multiply the number of electron volts by 1.6 times 10 to the minus 19, and that gives you the answer in joules. We're now going to look at the specific charge on an electron. The specific charge is, of course, the charge divided by the mass. Now, if you look again at my video on electromagnetism, you will see that if you put a charge in an electric field, so we take two plates, one of them negatively charged, one of them positively charged, and you put an electron in that field. The electron, of course, is negatively charged. It will move towards the positively charged plate. So far, so good. But if you now put a magnetic field into the paper, remember we show it as an arrow going away from you. If it were an arrow coming towards you, you would just see a point. But this magnetic field is going into the paper. Then that will cause the electron to go in a circular orbit. Now, if you adjust the magnetic field so the electron goes round actually in a complete circle, and you will have to vary the magnetic field until that happens, then what can you say? Well, anything that goes round in a circle must have a centripetal force that is keeping it in that circle. And a centripetal force is mv squared over r, where v is the velocity of the particle, and r is the radius of the circle, and m obviously is the mass of the electron. But we've also shown in the video on electromagnetism that the force that keeps a charged particle going round in a circle in a magnetic field is B, E, capital V, where B is the strength of the magnetic field, E is the charge on the electron, and V, sorry, that should be a small v, it's not voltage, that is V, that is also the velocity of the particle going round in a circle. But we also know that the energy of an electron, that's E capital V, this is now voltage, is equal to half mv squared, that's a little v, that's velocity. So that's the energy expressed in electron volts, that's the kinetic energy that is the equivalent. And we're going to use these two equations to derive the ratio of the charge to the mass. And the way we do it is to take this equation here and multiply both sides by r. So we now get mv squared equals be little v times r. Then by rearranging we can say E divided by m, put that on that side, is equal to v squared divided by bvr. And since the v cancels, that equals v divided by br. Now square both sides. E squared over m squared equals v squared over b squared r squared. And now from this equation, v squared equals 2e capital V divided by m. And we're going to substitute that v squared for that v squared. So now we get 2ev over m b squared r squared. And now that e will cancel one of the e's here, that m will cancel one of the m's there, and so now you've got E divided by m equals 2 capital V divided by b squared r squared. And that is a formula for the charge divided by the mass, the specific charge, and it's expressed in terms of the voltage, which you know, the magnetic field, which you know, and the radius of the circle that the electrons are going round, which you know. But unfortunately that only tells you the ratio of the charge to the mass. We want to know what the actual charge of the electron is, and then we will be able to work out the mass of the electron. And it was Millikan who did this in what was called the Millikan oil drop experiment. Millikan took two plates. One was positively charged, one was negatively charged. And there was a very small hole in the plate, and he had what's called an atomizer. You can almost think of this as almost a kind of spray can. And as it sprays out little molecules, little atoms, they get a very small charge on them, an electric charge. And of course, since they will have a mass, and since gravity acts on them, they will fall. We haven't got this plate switched on yet. There's no charge on the plate yet. So simply under gravity, they will fall. But they don't continue to accelerate because they eventually reach what is called a terminal velocity. This is because they are essentially moving through a fluid. The fluid is air. And the atoms of the air, the molecules of the air, will interact with this falling particle and slow it down to a point where it is still being accelerated, but the resistance of the air is equaling or balancing the gravitational pull. And at that point it reaches what's called a terminal velocity. It doesn't accelerate anymore. Now, according to Newton's second law, F equals ma, if there is no acceleration, then there cannot be a resulting force. And that means that the force of gravity that's pulling this down must be equaled by the force, what we call the viscous force, of the air, which is acting upwards. So you've got two forces. Gravity is acting down, the viscous force is acting upwards. The two are exactly balanced, and so the particle falls at constant velocity. Now, we don't need to prove this, but it just so happens that the force, the viscous force, is given by 6 pi eta RV, where pi, of course you know, eta is what's called the viscosity of air, r is the radius of the particle that's falling, and v is the terminal velocity. When it's no longer accelerating, that's its terminal velocity. And since the viscous force, which is pushing upwards, equals the gravitational force acting downwards, that means that mg, where m is the mass of the particle, must equal 6 pi eta RV, which is the force acting upwards. So what is the mass of the particle? Well, we know that density is mass divided by volume, which means that mass is equal to volume times density. For all practical purposes, we can think of this as a sphere. What is the volume of a sphere? It's 4/3 pi r cubed, where r is the radius of the sphere that this particle consists of. The density of the material will be known, and that's given by rho. So volume times density is mass. Multiply that also by g, so that's now mg, is equal to the viscous term, 6 pi eta RV. And if you rearrange this term for r, you've got an r cubed term there and an r term there, so they will cancel out to leave you with an r squared. And if you then put everything else on this side of the equation, you're going to get 6 pi eta v, because the r has gone, divided by everything on this side of the equation, which is 4/3 pi rho g. And that simply tidies up to 9 eta v, because the pi's cancel out, divided by 2 rho g. And now we're going to ask ourselves the question, what happens when we turn on this field? Remember, what we've got is, before we turn the field on, this particle is falling. It reaches a terminal velocity. When it's at the terminal velocity, its gravitational force downwards is being balanced by the viscous force upwards, and that means it doesn't accelerate anymore, but it continues to fall at a constant velocity. If we now switch the plate on, and the top plate is positively charged, and this particle is negatively charged, there will now be a force that will encourage that particle to go upwards. So it's moving down at constant speed, but now when the plate is switched on, it will want to move upwards. And we want to know what the interaction is going to be between the terminal velocity going downwards and the force that's now acting to try and get this thing to come back up to the top plate. Well, a quick reminder from the electric part of our course that if you have two plates, you put a negatively charged particle, maybe an electron, then that electron will be attracted to the positive plate. The force will equal the electric field, which is essentially the field that operates between the plates, multiplied by the charge on the particle, and the field is equal to the voltage across the plates divided by the distance between the plates. And that gives you that the force is V, the voltage, times Q, the charge, divided by d the distance between the plates. Now, we adjust the electric field here such that the particle is stationary. When it's stationary, there is no more viscous drag, so we can forget about viscosity because it's not falling, it's actually stationary. And when it's absolutely stationary, what can you say? You can say that the gravitational force that would want it to move downwards must be being balanced exactly by the electric force that's trying to make it go upwards. And those two must be exactly equal. Because it's stationary, there's now no viscous force. So we said that the force that is being caused by the electric field is VQ over D, where V is the voltage between the plates, Q is the charge on the particle, and D is the distance between the plates. And that must be being balanced by the gravitational force downwards. This is the force upwards because the positively charged plate is at the top. This is the force downwards. And what is the mass? Well, as before, it's the volume, 4/3 pi r cubed, times rho times g. Now, I don't need to rearrange this equation, but I think you can see that VQ over D equals 4/3 pi r cubed rho g. The only thing that is unknown in that is Q. We know the voltage between the plates, we know the distance between the plates, 4/3 pi, of course we know. R we calculated when the particle was in terminal velocity, that was the earlier part of the calculation. Rho is simply the density of the material, and G of course we know. So the only thing we don't know is Q. And what Millikan did was to repeat this experiment over and over again, and he measured the value of Q, that is the charge on the particle that he effectively got stationary because he'd got a electric force acting upwards that was exactly balanced by the gravitational force acting downwards. And he measured Q. And what he found was he did this many, many times, and of course he would have a whole variety of different charges on those particles, but he always found that it was a multiple of 1.6 times 10 to the minus 19 coulombs. You never got a charge that wasn't a multiple of that amount. And he concluded that that must be the basic or fundamental charge. And that must be the constituent charge of anything, and that is the charge on an electron. And it may be that there are 2, 3, 4, 10, 20, 50 electrons on one of those charged particles, but you always had to have charge in whole number multiples of this charge here, which is the now known to be the charge on an electron.